Hello, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to begin looking at a little bit of the mathematics that is involved with solids, and that of course means calculations of surface area and volume. So we're going to spend the next couple of days looking at surface area, and then a couple of days after that moving into volume, and that will wrap up the unit for us. So our title today is Surface Area of Prisms. Our objective, the student will learn to calculate the surface area of prisms. So obviously we're going to be working with the shapes that have two bases, not one. We'll come back and we'll work on those calculations next time. As always, anytime you need more time to copy something down, hit pause and then press play when you're ready to move on. Okay, so let's get started. Now, first off, basic generic definition here for surface area is the amount of stuff required to cover a solid. Now, we say stuff, whatever it is. It can be any units of measure, millimeters, centimeters, miles, inches, yards, gummy bears, whatever. Okay, that is surface area, the amount of stuff required to cover a solid. Now, we will run into a lot of formulas, and in fact, there are some formulas out there that deal with the surface area of prisms. However, it's my personal opinion that some of the formulas are actually harder to deal with than simply finding the area of the polygons that build the solids. So that's actually going to be the strategy that I am going to show you, is finding the areas of all of the polygons that build the solid. In order to do that, you're going to need to employ a tactic that you probably already know about, or a topic that you already know about, and that is going to be unfolding the solid and looking at the net of the figure. Okay. Now, hopefully you're already familiar with the definition of a net. If not, there it is for you. A net is what you get when you unfold a solid and look at all of its pieces lying flat. So copy that one down, even if you already know it. A net is what you get if you unfold a solid and look at all of its pieces lying flat. Okay, so let's take a look at some. Okay, we'll start off with probably what's the most basic of the prisms, which is a rectangular prism. And let's say we are asked to find the surface area. Now, what we're going to be doing here is, after you've got this figure copied down, the basic strategy is this. Okay, first off, and probably what's most important, is remember that solids are three-dimensional objects. Even if the figure is not drawn so that you can see the edges that are hiding behind the figure, probably a good idea for you to draw them in for yourself, just to remind you of the fact that there are some polygons that are hiding from our view. They're being blocked by other sides of the solid that happen to be in front of them. Okay, so by drawing in where the edges of the solid should be, as if we were able to see through the solid, that can help us keep us from forgetting some of the shapes that might be back there. Okay, so that's our first strategy. If the edges are not all completely drawn in, we are going to draw them in so that we can see where all of our polygons are. Okay, now what you're going to do is we are going to convert this solid from being a solid into being a net of the solid. And that basically amounts to allowing the figure to kind of fall apart, for lack of a better way of putting it, so that all of the sides will lay down flat. Okay, I always think of it like if you've ever built a house of cards, playing cards where you're stacking them on top of each other, you end up with something that is a three-dimensional solid but of course the house of cards eventually all falls down and you end up with all the little rectangles kind of all over the table. Well, that's your net right there. Okay, but we're going to do this in such a way that no polygon lays on top of another polygon. That means that the roof of your solid is going to have to swing out of the way. We cannot allow it just to drop straight down onto the floor of the prism. It's got to get out of the way so that they can each have their own space laying down on the table. Okay, so when you unfold a rectangular prism, it is likely that you might get something that looks like this guy. And I have labeled the 6 different sides from the net when it turned, or from the solid when it turned into a net. And it might not be a bad idea for you to do that, especially if you develop a little bit of a habit of losing some of your sides. If you start off with 6 sides on your solid, you better end up with 6 polygons in your net. By labeling them, it'll be real easy to see which one might be missing and not counted yet. Okay, so that's your second strategy, is to construct your net from your solid. Now the next thing you're going to need to do, and this is critical to figuring out the surface area calculation correctly, is transfer your information from where it was in the solids, the measurements on your solid. They were attached to certain edges somewhere in the solid. Well, when you allow your solid to fall apart and turn into a net, well, those edges are still in your picture somewhere. We need to put the measurements back into the figure wherever they were attached. Okay, so in this particular case, the 4 inches was across the very front edge of the solid, so there it is attached to our floor across the front edge. The 3 inches was the front to back on the solid. Okay, so there it still is attached to the floor of the solid. And the 2 inches was the height of our solid. Okay, well, that height, that edge that was attached to, kind of broke in half, and part of it went with the front of the solid, and part of it went with the left side of the solid. So I just kind of put it in there in between the front and the left side of the solid. So there's the measurements, kind of similar to where they came from in the original picture of the solid. Now, obviously, there are 6 polygons that were in our solid. Okay, so if you're thinking, man, I got to find the area of each of these individual polygons separately and then add them all up, I'm going to be doing math all day long just to get my surface area done. Well, it's not actually that bad, because in your prisms and in your pyramids, you'll see as well, a lot of the polygons end up being repeated, some of them several times. So all we really need to do is kind of figure out which polygons are going to be congruent to other polygons from the figure, and we don't have to figure out those areas separately. Once we know one of them, we'll know the other one that matches it. Okay, so actually in our rectangular prism, there are only 3 different areas that need to be found, and I color code mine whenever I'm working problems like this. So there's actually 3 different areas. The floor and the ceiling of the rectangular prism were the same. I've got those in the lime green there. The left side and the right side of the prism were the same. That's the light blue there. And the front wall and the back wall were the same. That's the yellow. Okay, so all I'll really need to do is find 3 different areas of 3 different rectangles, and that is not a difficult chore. Okay, so let's actually get to that. Let's take a look at the calculations. Okay, so individual areas. I even have mine labeled from the figure, area 1, area 2, area 3. That way, if I get lost in the middle of the calculations, I can remember what I have done and what I have not done. I'm just going to start off with area 1. And I go, okay, area 1, what kind of a shape was it? Oh, it's a rectangle. Okay, rectangles have a formula. How do you find the area of a rectangle? Rectangle is base times height. So I just look back at the figure and go, okay, what are the base and the height of area 1? Well, looking into the diagram, we can see that that front edge going across the area 1 from left to right is 4 inches. and the top to bottom measurement along the side there is 3 inches. So we have a rectangle that is 4 by 3. So I'm going to plug those numbers into my formula, 4 by 3. And 4 times 3 is, of course, 12. And then you go, oh, but wait a minute, there's two sides, or two polygons like area 1, so I'm going to double it. I'm going to take that 12, multiply it by 2, and I've got 24. Now, that's not the answer to the problem. That's just a piece of information that we need, but we're going to do it again. Then we go, okay, the next one would be area 2. Well, let's look at area 2. What kind of shape is area 2? Hey, it's another rectangle. Cool. Rectangle is base times height. What are the base and the height of area 2? Well, over on the right side, we find one of the side measurements is 3 inches. And from the area 2 over on the left side, very easy to see that the other measurement is 2 inches. So we got a rectangle that is 3 by 2. So again, just plugging that in. 3 by 2 is, of course, 6. And there are two sides that are like that one. So we're going to take that 6, we're going to double it, and we get 12. And once again, that's not the answer. That's just some information that we need. Let's keep working. Area 3 is another rectangle. So we go, okay, area 3, you're a rectangle. That means you're found by base times height. What are the measurements of area 3? Well, it's 4 inches across from left to right and 2 inches from top to bottom. So it's a 4 by 2 rectangle. So plugging that in, 4 by 2, okay, that is 8. And of course, there are two rectangles like that one. So we're going to take that 8, we're going to double it, and we get 16. Now that is 6 different polygons that have been accounted for. 2 rectangles, then 2 more rectangles, then 2 more rectangles. That's 6. There were only 6 sides in the polygon, so we should have it all taken care of. Now all you have to do is combine all your areas. You take your 24, you take your 12, you take your 16, you add them all up, and that is 52. Okay, and it is 52 square inches. Remember, area is a second dimensional measurement. It has length and it has width. That is 2 dimensions. So all of your units of measure for surface area will be something squared. Okay, now it's not usually so much thinking. Okay, it'll become second nature for you. Find the surface area for the triangular prism shown below. Well, it's going to be the same strategies over and over each time, and then all you have to do is find the areas of the different polygons. Well, have a look at it. What's the first strategy? First strategy is going to be to draw in any edges that happen to be hiding from us. Then we will look at the net, and then we will look at the different areas. Okay, so let's take our triangular prism here and let's construct the figure. Let's see if there's any edges hiding from us. Now, it says that this figure is a triangular prism. Well, prism means that there are two bases. Okay, so somewhere is a base that is hiding from us because we cannot see any sides that are parallel and congruent to each other yet. Okay, and the problem says that the base is triangular. That means that this triangle that's looking at us on the front side, that's one of the bases. It means that on the back side there should be another triangle that's hiding from us. So when we draw in our edges, we would want to make that triangular prism part of it come true. Okay, so drawing in the edges, that's what our figure would look like if we could see through it. Second step is to look at the net. So we're going to take our triangular prism here, we're going to break it apart at the edges and let all the pieces fall down and lay down flat. So our net might look something like that guy. Now, it's not necessary that it be kind of rotated like mine is. You can absolutely draw it, with the rectangles straight up and down. I was just kind of trying to position it the same as it would have been from the solid above. Okay, but anyway, there's what the net looks like. Very clearly, we can see that we have two triangular bases and 3 rectangular lateral faces that we're going to have to figure out. Okay, so let's take a look and see what sides are going to be similar, or I'm sorry, congruent to each other. That means we need to get some measurements going. Okay, so taking the measurements from the original solid and plugging them into our net, we have measurements in these locations, straight from the solid, just writing them down next to the edges that they came from in the solid, writing them down here in the net. Now, by comparing the measurements, obviously we have two base triangles that are going to be the same, and we have three rectangles. But a quick check of the measurements on the side lengths of the rectangles, none of these rectangles are congruent. So we're actually going to end up with 4 different areas that we have to figure out, 2 triangles that are the same, and 3 rectangles that are different. Okay, but none of these calculations are particularly difficult. All we got to do is figure them out. So let's get started. Area 1 is a rectangle. So once again, our rectangle is found by going base times height. So let's look at area 1, and let's find the base and the height of that rectangle. Well, it looks like the measurements of that rectangle are going to be 6 meters and 4 meters. Okay, so plugging in 6 and 4, of course 6 times 4 is 24. There's only one rectangle like this, so we're not going to double it or anything like that. 24 will simply become part of our answer. Okay. Area 2, uh-oh, went the wrong way, sorry. Area 2 is another rectangle. Okay. And let's see if we can't find the measurements of area 2. Looks like its measurements are going to be a 6 and a 3. Okay, so 6 and a 3 for that rectangle. Obviously 3 times 6 is 18. Again, there was only one rectangle like that, so 18 will be part of our answer. Area 3, I went the wrong direction again. Area 3 from our diagram is another rectangle, and the measurements of that rectangle are 5 and 6. So 5 times 6 is 30. There's only one rectangle like that, so 30 will become part of our answer. And then finally, I keep clicking the wrong button, we have area 4. Okay, area 4 is a triangle. There are 2 of them like this. Okay, but area 4 is a triangle, so we need to know the formula, 1/2 times base times height of the triangle. So let's see if we can get the base and the height measurement of the triangle. Looking at that bottom triangle, very clearly to see there that the measurements are 3 and 4 for the base and height of the triangle. So we'll plug that in, 3 and 4. 1/2 times 3 times 4 is 6. Now there are 2 triangular bases like this one, so we'll take that 6 and we will double it, and we will get 12. And just like before, all we have to do, add up the numbers. 24 and 18 and 30 and 12 is 84. The units of measure were meters squared, or they were meters. We're dealing in area, so it is meters squared. We're going to take a look at one more figure here because it's kind of a special case, and it is the cylinder. A lot of times when tests ask us questions about surface area, cylinder is at least one of them. And if they only ask one surface area question, the tendency is for them to ask about the cylinder, so we better make sure we understand it. Find the surface area of the cylinder below. Well, obviously, you can see the cylinder there and the measurements that are provided. The thing that makes the cylinder the challenge is understanding what the net is actually looking like. Okay, well, the problem is this: the surface or the lateral face of the cylinder is continuous. There is no beginning and there is no end to the side that wraps around the circular bases. So what you actually have to do is kind of split open one side of the lateral face and unwrap it from around the circular bases. And what you're going to find is that the lateral face is actually a rectangular shape that just kind of joins together with itself on one of its edges. Okay, so basically what we have, as you see there, surface around a cylinder is a rectangle, and its length is equal to the length of the circumference of the circular base, which is to say that rectangle is exactly long enough to reach around that circle one time, that circumference. Okay, so we have a net that looks like this guy, and we transfer the measurements from the solid to the net. Okay, we had an 8-foot circumference or 8-foot diameter on the circular bases, and we had 10 feet in between the circular bases. So there those are. And obviously we have two circular bases that are going to be congruent to each other, and then we have a rectangle. Okay, well again, the formulas are not very difficult. We just need to work them out. Okay. So obviously, area number 1 is a circle. Circle comes with an area formula. It is pi times the radius squared. So all we need to know is the radius. Well, looking back at the figure, we have a diameter of 8, so that means the radius must be 4. Okay, so plugging into the formula, okay, and I went ahead and did 3.14 on this, okay, even though we haven't really been doing 3.14 on our calculations, okay, but we're going to end up with some decimal points on this stuff, and that's okay. But we get an answer in the ballpark of 50.24, and of course there are two of the circular bases, so we'll take that 50.24 and we will double it, and that is 100.48. Area 2 obviously is the rectangle. Now, clearly on the rectangle, which is going to be base times height, we have one of the side measurements. It's the 10 feet that was between the two circular bases. But then we need to know what the width of this rectangle is. Now, as we've already said, the width of the rectangle is exactly long enough to reach around the circle one time. That is circumference. So circumference of a circle is found by 2 times pi times the radius. Okay, so plugging into the formula, we should have, instead of base times height, we have 2 times pi times radius times height. Okay, now plugging in the values that we know, we know that the radius is 4, and we know that the height is 10. And when we run through all these decimal points, what we end up with is 251.2. Okay, now there's only one of these rectangles, so all we're going to do is we're going to take that 251, we're going to combine it with the 100.48 from above, and that is 351.68, and it's square feet. Okay, so you kind of get the idea here. Surface area is it's just one of those where there's a lot of different ways. The problems can be kind of an infinite number of problems. We could spend all day working surface area problems and still never really put a dent in it. So it's just each surface area problem is different according to what the solid looks like and how many shapes there are and what kind of shapes there are and so on. You just have to adjust as you go. Anyway, I appreciate you finding time to get your notes taken care of. I apologize for the video running a little bit long, but I'll see you in class.